Section 4.5. In Section 4.5, we are going to solve both exponential and logarithmic equations. So let's start with the exponential equations. These exponential equations, some are simple and some can get rather involved. So this first type here are some of the simpler ones, okay? And these are simpler because we can match the bases, all right? So we're going to use a property. If base u raised to the u power equals some base raised to the v power, all right? So if we have the same exponential base raised to different powers, then what we know is that if the bases match, then the exponents have to be equal, all right? So in the first example, we have 5 to the x equals 125. Now, at first glance, these bases don't match, but 125 can be written as base 5, because 125 is 5 cubed, right? 5 times 5 times 5. So I'm going to rewrite this equation, right? So on the left-hand side, we get 5 to the x, and then 125 is 5 cubed. Right, so here we have this equation where the bases are the same, and if the bases are the same, then the exponents have to be equal, right? So I'm just going to cancel these bases and say x equals 3, and there we have that equation solved. So if you can match those bases, do so, okay, and the resulting equation will be the exponents equaling each other. So if you look at the next example, 5 to the 2x equals 5 to the x plus 1, the bases already match, right? So if the bases match, then for this equation to be equal, the exponents have to be equal. So we're going to cancel those bases out, and we get 2x equals x plus 1. And here's a simple linear equation, right, we can solve. So I'm going to subtract x from both sides, and I get x equals 1. All right. So if we plug 1 into the original problem, we get 5 to the second power equals 5 to the second power. Okay, and of course that's true. So if the bases, if you can make them match, do so. All right, and then you can just set the exponents equal to each other. So the next type of exponential equations is if you can't make the bases match. So for example, we have 3 raised to the x plus 2 equals 7. Well, the base on the left is 3 and the base on the right is 7, and there's no way we can get those to match. All right, so if you can't get them to match, then we're going to have to use log or ln. So I'm going to rewrite this equation, 3 to the x plus 2 equals 7. All right, and so the first, part A asks for the exact solution expressed in terms of logarithms, and part B asks for the decimal, okay, approximate it. So let's first find the exact answer, all right? So what we want to do here is we want to solve for x, and x is in the exponent up here, and we can't solve for x when it's in the power, all right? So we need to bring this x down on the main line, if you will. Right, and so we're going to use that third law of logarithms. And so what I'm going to do is I'm going to ln both sides. You can log if you'd like, but I'm going to always use ln here. And so if I ln both sides, now I have this. Okay, but this helps because I can use that third law that says the power gets pulled down out front. All right, so by taking the ln of both sides, that allows me to bring this x down on the main line where I can solve for it. All right, now this exponent here, x plus 2, is more than one term. So I want to make sure I put it in parentheses. So I have x plus 2 out in front of ln of 3, and that's going to equal ln of 7. All right. So now I want to solve for the x, right? The x is inside the parentheses. So first what I need to do is I need to divide both sides by ln of 3 to get those parentheses by themselves. All right, so now I have x plus 2 equals ln of 7 divided by ln of 3. And then solving for x, I'm going to subtract 2 from both sides. So I get x equals ln of 7 divided by ln of 3 minus 2. All right? And that's going to be my exact solution. Right? We're not going to, we can't simplify this, right? Because we can only combine it if the argument is being divided, not if the ln's are being divided. And so this is as simple as it gets, right? This is the exact solution here. That's what they're going to want if they ask for the exact solution. They want you to go ahead and leave the ln's and the logs in there, all right? So on B, use a calculator to find an approximation rounded to 6 decimals. That's when you can start plugging it into the calculator and finding the result. So let me go ahead and do that. So I have my calculator here, right? We're going to do ln of 7. ln 7, remember to close those parentheses, divided by ln of 3, close those parentheses, and then I want to subtract 2. Okay? And it says round to 6 decimal places. So 1, 2, 3, 4, 5, 6. The 6th decimal place is a 6. The 7th decimal place is a 2, and so the 6th decimal place is going to remain a 6. So I get an approximate solution, negative 0.228756. Right. Next, all right, let's solve this equation. 8e to the 2x equals 20, right? So this one here is not just an exponential equaling a constant, okay? The exponential expression is just e to the 2x. The 8 is a coefficient. So what we're always going to do first, before we tackle this exponential part of the equation, is we're going to isolate the exponential expression. Which means, we want to get the e to the 2x part of the equation by itself. Okay, so the first thing we're going to do is we're going to divide both sides by 8 to get that e to the 2x by itself. So now I have e to the 2x equals, and I'm going to go ahead and reduce this. Okay, 20 and 8 reduced by 4. So I'm going to get 2 on the bottom and 5 on the top. So I get 5 halves here. All right. So now I have e to the 2x equals 5 halves. I have the exponential expression all by itself. But the x is in the exponent again. So what I want to do is I want to be able to bring it down. Okay, so I'm going to ln this again to bring the exponent down. All right. That's always what I'm going to do when the x is in the exponent. So now I get 2x times ln of e equals ln of 5 halves. Right? So if you remember, the natural log ln is base e already. So ln and e cancel to leave us, cancel to 1, if you will. You can type that in your calculator if you'd like to confirm that. ln of e equals 1. All right? So we get 2x times 1 here. So I just have 2x equals ln of 5 halves. All right? Now to solve for x, I need to divide by 2. Okay? So the exact solution for x is ln of 5 halves divided by 2. All right? Now if you wanted to find the decimal approximation for that, let me go ahead and plug it in so that you can make sure you know how to plug it into your calculator. All right, I got 0.458145. Okay, so when you plug ln of 5 halves divided by 2 in the calculator, make sure you are closing the parentheses after the 5 halves and then dividing by 2. Okay. All right, so on the next one it says solve the exponential equation algebraically and graphically. I'll briefly show you the graphical way, but I really want you to focus on solving it the algebraic way. Okay, so we have e to the 3 minus 2x equals 4. So in this equation, the exponential expression is here, e to the 3 minus 2x. There's no constant out in front, so it is already by itself. Okay, so we're ready to get this x down on the main line where we can solve for it. So I'm going to take ln of both sides. Now this time, instead of canceling the ln and e secondary, I'm going to go ahead and let it cancel here. Okay, because ln of base e cancels, and so we just get 3 minus 2x equals ln of 4. Right. So now solving for x, 3 minus 2x equals ln of 4, we need to subtract 3 from both sides first. And so we're going to get negative 2x equals ln of 4 minus 3. And then divide by negative 2. So we get x equals ln of 4 minus 3 divided by negative 2. Oops, sorry. So if I were to plug that into the calculator, okay, we have to be really careful because now we have two terms in the numerator. So I want to make sure I put those in parentheses when I plug it into the calculator. So I'm going to get, let's do it over here, ln, parentheses, ln 4. Remember to close the parentheses after the 4, minus 3. Close it around the numerator. Divide by negative 2 gives me approximately 0.806853 this time, because the 6 decimal place is a 2, the 7th place is an 8, so I need to round that 2 up. All right. So here is the algebraic way of finding the solution. Okay, ln it. That's going to cancel the e, but it also brings it down out front if you need to. All right, and then solve for the x, I get 0.806. So algebraically or graphically, what we do to solve this equation is we would graph both sides of this equation. We would put e to the 3 minus 2x as y1, and we would put 4 as y2, and that's going to get you a graph that looks like this. So I'm going to go ahead and do that for you. Okay, so I'm going to put e to the 3 minus 2x. That's going to be y1, and then I'm going to put 4 in. Okay, so I have the left-hand side in y1 and the right-hand side as y2. And then I'm going to go ahead and change the window to match this graph here. So the x value goes from 0 to 2. And it looks like they did the scale at 0.5, okay? And then the y values go from 0 to 5, and 1, 2, 3, 4, 5. They did just a scale of 1 there, okay? So now when I graph this, it's going to look exactly like the handout here. So there's our e to the 3 minus 2x, and then here's our y equals 4. So graphically, what we can do to solve this equation is we can find the intersection. Where does the 4 line intersect our e line? So calc is above trace, and we want to calculate the intersection. And then we only have 2 curves, and so when you calculate the intersection, it asks for the first curve. Anywhere on y sub 1 is fine. Okay, and then when you hit enter, it's going to ask for the second curve. Anywhere on y2 is fine. Hit enter, and it's going to say guess, and you go ahead and enter one more time, and it should take that cursor right to the intersection point. And so if you notice, okay, it's kind of hard to read, but it is 0.806853. Okay, so if you wanted to solve that graphically, you just graph both sides and then calculate the intersection. All right. Calculate intersection. All right, and we let y1 equal e to the 3 minus 2x, and we let y2 equal 4. All right, and we just calculated the intersection using second trace. All right. Okay, so the last exponential equation type is here. So we have 3x e to the x plus x squared e to the x equals 0. Now this looks complicated, but I assure you it's not. All right. So what we're going to do is we're going to factor this. The first thing I'm going to do is I'm going to factor e to the x out because there's an e to the x in both terms. So I'm going to get e to the x times 3x plus x squared equals 0. Okay. Now, if you notice 3x plus x squared, that factors, right? So I'm going to go ahead and factor that as well. All right. So this is just two terms, and so we're just going to factor by taking out the greatest common factor, and so there's an x in both of these terms. So I'm going to get e to the x as my first factor, and then if I take an x out, I'm left with 3 plus x. All right, so I just kind of factored it into three separate factors. This is x times 3 plus x, if you will. All right, so I have e to the x times 3 plus x equals 0. None of these factors factor any further. So what I would need to do to solve this equation after it's factored is to set each factor equal to 0. So I'm going to get e to the x equals 0, then the x equals 0, and then the 3 plus x equals 0. All right, and we're going to solve each one of those. So the middle one's easy, right? This one's already solved. This one's easy too. We just need to subtract 3 from both sides. Okay, so we get x equals -3. Okay. Now, when we set e to the x equal to 0, x is in the exponent, right? So I'm going to ln this function to cancel the e, and I get x equals ln of 0, right? And so we have to remember what the domain of our ln functions are, right? The argument here has to be positive. It can't be 0, and it can't be negative. So what I want to do is on the calculator, I want to show you, right? If I type in ln of 0 and hit enter, it's going to give me an error, okay? It's going to give me a domain error because the argument can't equal 0. And so what we're going to do here is this equation has no solution, right? So the other way you can think about this is we have the exponential function equal to 0. And if you remember the graph of the exponential function, right, it has an asymptote at 0. It's going to get close to 0, but it's never going to equal 0. So this equation here has no solution because this graph is never going to reach 0, right? So two reasons why e to the x can't equal 0. So this equation has two solutions, right? Even though it had three factors, only two of the equations worked out. So we're going to get x equals 0, comma, -3. All right, two solutions for that equation. So those are all the different exponential equations you will encounter on the homework. So let's move on to solving logarithmic equations. The key to solving logarithmic equations is to make sure you have one log equaling one log. All right, so we want to condense each side of the equation before we start. All right, can you see that? All right, condense each side of the equation because we want log something equals log something. All right, you want one log on each side before you start to cancel them out. All right, so on the left-hand side of this equation, we only have one log, okay, log of x squared plus 1. On the right-hand side, we have two logs. So what we need to do is we need to add these together, okay? So remember how you add logarithms, okay? How do you add logarithms? You multiply the arguments together, all right? So if I write this as a single log here, I need to multiply x minus 2 times x plus 3. So if I do that over to the side here, x minus 2 times x plus 3, let's go ahead and FOIL that out. We're going to get x squared plus 3x minus 2x minus 6. So if I combine the middle terms here, I'm going to get x squared plus x minus 6. Right? So if I add these two logarithms together, I'm going to get log x squared plus x minus 6. All right? And then we didn't do anything to the left-hand side, so this remains log x squared plus 1. Okay? So now what we're going to do is the x that we're looking to solve for is inside the logarithm. So we want to cancel these logarithms. So what cancels logarithms? The exponential expression of the same base. So this log doesn't have a base, right? And so if it doesn't have a base, it's understood to be base 10. Log x is the same thing as log base 10 of x, right? But they're never going to write log base 10. They're just going to write log. So you have to remember that this is base 10. Okay, so I'm going to take 10. I'm going to raise both sides by it. And that's going to cancel the logarithms on both sides. So now I have x squared plus 1 equals x squared plus x minus 6. And now I have an equation that I can solve. Okay, so the first thing we're going to do, let's go ahead and get everything on the same side. So if I subtract x squared from both sides, they just cancel out, right? So now I have 1 equals x minus 6. So I'm going to go ahead and leave the x on the right-hand side, add 6 to both sides, and I get x equals 7, right? Now, what you have to do with logarithms, there's an extra step, okay? You always want to make sure that your answer is in the domain, right? Because remember, we can't take a log of a negative number or a 0. So you want to make sure you check this, right? So take this 7, plug it back into the original equation, and just plug it into the argument. Make sure the argument remains positive. So 7 squared plus 1 is 50. That's okay. 7 minus 2 is 5. That's a positive number. 7 plus 3 is 10. That's a positive number. So all these arguments stayed positive. Okay, so I did check this, and this is a solution. Had 7, when I plugged it in, made one of these arguments negative, I would have to throw it out, and there would have been no solution to this logarithmic equation. Right? So make sure you're checking your answer on a logarithmic equation. All right, so let's look at another one. Okay, here's a natural log, right? So on this one, we want one log on each side, but the right-hand side doesn't have a log, but we do have one log on the left-hand side, okay? So we're going to skip the, make sure we have one log equaling one log. One log equaling 0 logs is fine as well, all right? So I'm going to rewrite this. Ln of x equals 8, just so I can write it bigger, okay? And I do like to keep that argument in the parentheses. So what we want to do here is the x is in the argument of ln. Okay? In order to solve for it, we need to get it out of this argument. So I need to cancel ln, right? So what cancels ln? E, right? So we're going to e both sides. Because remember, ln of x is the same thing as log base e. So the exponential that cancels ln is e, right? But you're never going to see it written log base e. You're always going to see it written ln, all right? So e and ln cancel each other out, so we get x equals e to the 8th power, right? And this one's done because that's what x equals. If you need to plug it into the calculator, that's fine, right? So here's another one, okay, that doesn't have one log equaling one log. It has one log equaling a constant, which is fine. Okay, you just can't have more than one log on one side of the equation, right? But the x is in this argument, right? So we need to cancel this log base 2. What cancels log base 2? Raising by the exponential 2. Okay, so I'm going to raise both sides by 2 here. 2 raised to the log base 2 cancels, and I get 25 minus x equals 2 to the third power, right? So 2 to the third power is 8. So I have 25 minus x equals 8. And if I want to solve this for x, I'm going to go ahead and subtract 25 from both sides. So I get negative x equals negative 17. And so then I'll divide by a negative 1, and I get x equals 17. Right? Oh, you know, I forgot to check the previous one. Let's go ahead and do that. Let me zoom out. Okay, e to the 8th, very positive number. All right? And so if I plug e to the 8th in here, it's actually kind of an easy check. ln of e to the 8th. Right? ln and e are going to cancel, and we're left with 8 equals 8, which is good. Okay? But e to the 8th is a very positive number, and so it's going to keep this argument positive. Right? What about 17? Does it keep our argument positive? 25 minus 17 is 8, and so we're good there. All right? This one checks as well. Right? So next type here, we have 4 plus 3 log 2x equals 16. Right? We need to condense this as much as possible, right, before we start canceling our logarithm. So I want to get 1 log equaling a constant, all right, or 1 log equaling 1 log, but that's not possible here. So the first thing I'm going to do is I'm going to subtract 4 from both sides. All right, so I have 3 log 2x equals 12. Right? So now what I want to do is I want to get the log by itself. So I'm going to divide by 3. And so I have log 2x equals 4. Okay, get that logarithmic statement by itself, right? Isolate the logarithmic expression. So now that we have 1 log equaling a constant, now I can focus on canceling the log. Right? We can't cancel a log if it has a coefficient or constants being added and multiplied to it. So what cancels log? It has no base. So it's understood to be base 10. Right? So 10 raised to the log cancels. We get 2x equals 10 to the 4th. Right? So remember 10 to the 4th is a 1 followed by 4 zeros. So 4 zeros gets us 10,000, right? So if I divide by 2, I get x equals 5,000, right? Now that's a pretty large number, but go ahead and plug it into the original equation. Okay, the only argument we have here, 2 times 5,000 is positive 10,000, so that seems to work as well. Okay, so let's check it. Circle it and check it to make sure you've checked those answers. All right, so let's do this example here. Okay, solving this equation algebraically and graphically. I probably am just going to do the algebraic one here. All right, so we have 2 logs on the left-hand side. And no logs on the right-hand side. But our goal is, okay, our have to is only 1 log on each side, okay, or 0 logs. And so I need to combine these, right? I need to add these logarithms together. And how do you add logarithms together? You multiply the arguments, right? So I need to multiply x plus 2 times x minus 1. So let me go ahead and do that over on the side here. So I get x squared minus x plus 2x minus 2, x squared plus x minus 2. So by multiplying these arguments together, I got x squared plus x minus 2. So when I add these 2 logarithms together, I'm going to get log x squared plus x minus 2 equals 1. So now I have 1 log on the left, no logs on the right, but that's okay. All right. So I want to cancel the logarithm. So I'm going to raise what cancels log, okay, for like the umpteenth time tonight, right? A 10. So we're going to do 10 to the log cancels. We get x squared plus x minus 2 equals 10 to the first, right? So what we have to do here is we have to solve this. This is a quadratic equation. The only way to solve quadratic equations is to get it set equal to 0, right? Don't start factoring it here. Move this 10 over, right? So I'm going to subtract 10 from both sides, and I'm going to get x squared plus x minus 12 equals 0, right? Set that quadratic equation equal to 0 before you try and before you solve it, okay? So to solve this one, we can factor, or we can use the quadratic formula, but this one does factor, okay? What multiplies to negative 12 adds to 1. 4 and 3 are those magic numbers, right? But we want a positive 4 and a negative 3, okay? So this is the polynomial factored, and so we have two factors. So to solve, we want to set both factors equal to 0 and solve. So I'm going to subtract 4 from both sides to solve the first one. And I'm going to add 3 to both sides to solve the second one. So I have two solutions, negative 4 and 3. Okay, but we want to check these. Right? Make sure you're doing that check. Right? So if I plug negative 4 into the original equation, which is here, negative 4 plus 2 is negative 2. Right? That makes this argument negative. So this cannot be a solution. We need to throw this answer out. Right? It can't make anything negative. So then let's check 3. If I plug 3 into the argument, 3 plus 2 is 5, which is positive. 3 minus 1 is 2, which is positive. And so this is the only one that checks. Right? So even though we had two solutions initially, only 3 worked. Okay? So to solve this algebra or graphically, what we would do is we'd probably, trying to see what they did here. I think they brought everything over, okay? I think they did log x plus 2 plus log x minus 1 equaled 0. All right, they did log x plus 2 plus log x minus 1 and set it equal to 0. Because it looks like they're trying to show that that solution is at 3. Now we could have very easily left the 1 over there and just plugged in the left-hand side and the right-hand side in and calculated that intersection. All right. So I think that's what I'm going to do. Okay. I'm going to go ahead and show you this. I'm going to plug log x plus 2, put it in y1. Okay, so the left-hand side in y1. And then put the right-hand side in y2, right? So we have the left-hand side equaling the right-hand side. And then I'm going to change the window to match this again. So the x values are going from 0 to 6, and the y values are going from negative 3 to 3. Negative 3 to 3. Okay, and so if I graph this, we're going to get our logarithmic side here, and y1. We're going to get our constant here, and so where do they intersect? Right? Visually, if you were to zoom in here, you can see where that intersection point is right above 3. Okay, and here's our logarithmic graph. It's not going to come back down, right? So it only has one intersection point, so there's only one solution at 3. All right, so the next examples in our packet are the word problems, and I think I'm going to do that in a separate video.